A toolbox falls from a building. Its height, f of t, from the ground after t seconds is given by the equation f of t is equal to 100 minus 16 t squared. There are three questions that were asked. Part A says find the impact time, t star. So let's go ahead and talk about the solution for part A. Well, the impact time is going to be when the object hits the ground. And so if the height of the object from the ground is given by f of t, then when f of t is equal to 0, that means that the height of the object is 0 feet from the ground, which means that it's impacted the ground. Specifically, what we're looking for is what time makes this guy 0. So we're going to write it as t star. So that's what we're looking for. We want this t star value. It's not too hard to find. F of t star is equal to 100 minus 16 t star squared. That's this guy right here. Right? If we plug it in here, that's what we get. And we want that thing to be equal to 0. Okay, no problem there. So we need to solve for t star. We want to know what is this impact time. I want you to notice that I'm not always just writing equals between all of them. What I'm saying is that this thing implies this, which implies this, and this is going to imply something else. So if we keep solving, we get 100 is equal to 16 t star squared, which implies that t star squared is equal to, I believe that's 6.25. And that implies that t star is equal to plus or minus 2.5, but we're going to use the positive 2.5 and not use negative time. There it is. So at 2.5 seconds, the toolbox has hit the ground. Okay, so this is our solution for part A. Now let's take a look at part B. We need to find the impact velocity. So what we need is the velocity at the time of impact, the velocity at t star. So we need the velocity at 2.5. Well, what is that? Well, velocity is the change in the object's position over the change in the time. Now, particularly here, we're looking for an instantaneous velocity, and the reason that this is instantaneous is that we're looking for the velocity at an exact moment at the impact. So what is the instantaneous velocity? Well, the instantaneous velocity is given by the derivative of the position function at whatever time we're looking for. Well, we know there's a couple ways to do f prime at t star. The first way is to do the following. So we could take f at t star plus a little bit minus f at t star all over a little bit, and let that little bit become really small. Or we could use our quadratic rule. I'm going to do it the hard way. my recommendation is that you follow along, make sure you can do it the hard way, and then you try the quadratic rule and make sure that you get the same value out. So what do we have? We need f prime at 2.5, which is going to be f at 2.5 seconds plus a little bit minus f at 2.5. Oops, I put change of x. I should stay consistent and do change of t, because that's the variable that we're changing here, right? Right, t is the guy on the inside, so that's the guy that's changing just a little bit. Okay, so let's go ahead and solve this. This isn't too bad. The function f, if you remember, is equal to 100 minus 16t squared. Or a better way of writing that is f of something is equal to 100 minus 16 times something squared. So let's go ahead and compute these. So this is going to give us the following. Stay consistent here with my notation. So f prime at 2.5 is going to be equal to 100 minus 16 times 2.5 plus delta t squared minus, so ladies and gentlemen, that's this right here. Then we're going to subtract off f at 2.5, which is 100 minus 16 times 2.5 squared. And we're going to divide that by delta t. And this right here is this right here. Well, here's the nice thing. If you take 100 and you subtract 16 times 2.5 squared, this thing right here is the position, and we already know that that guy is 0, right? This tells us what is the height of the toolbox at 2.5 seconds. Well, that's 0. So this reduces quite nicely. Now this right here is not 0. Okay, so we got to do a little bit of computation there. But what we get is that f prime, the velocity at impact, is going to be equal to 100 minus 16 times 2.5 plus a little bit squared over a little bit. Because this guy right here, this whole thing is equal to 0. You check that out on your calculator. So let's go ahead and multiply this out right here. So it's going to be 100 minus 16 times. So I've got 2.5 squared, which we know is 6.25, plus 2 times 2.5, which is 5, delta t plus delta t squared. So this is going to be 100 minus, now 16 times 6.25 gives me 100. Whoops, I put plus, but you see it's going to have to be minus because I'm going to have to distribute. Right? So 16 times 5 is 80. Delta t minus 16 delta t squared over delta t. Now, right here, these guys cancel. And so we're left with negative 80 delta t minus 16 delta t squared over delta t, which tells me that f prime of 2.5 is equal to negative 80 minus 16 delta t. As delta t becomes really small, f prime at 2.5 is equal to negative 80. And this is a rate of change. It is your change in position over your change in time. So that's feet per second. So what does that tell us? Well, the answer is that after all of this, is that the toolbox is traveling at negative 80 feet per second when it hits the ground. So its velocity is negative because it's falling, right? It's going downward. Okay, that's really not what's important. I mean, the negative tells us the direction. Okay, but the 80 is what's important. So it's traveling at 80 feet per second. Now, what does that even mean? Well, look, you don't have to do this for this problem, but 80 feet in 1 second. If I multiply that by 5,000. Excuse me, if I take that and divide it by 5,280 feet in 1 mile, and then I multiply that by 3,600 seconds in 1 hour, because there's 60 seconds each minute, 60 minutes in an hour. We have 80 times 3,600 divided by 5,280 gives me 54.54 repeating miles per hour. So this toolbox, 80 feet per second, is roughly 55 miles per hour. So that makes more sense than this, because you know, driving in a car, what 54 miles per hour feels like. So now you know how fast that toolbox is traveling. And now, would you want to get hit with a toolbox traveling that fast? Probably not. Okay, so you can tell 80 feet per second, it tells me how fast it's going, but what's really nice is being able to convert it into something I know. You don't need to do that for this problem, though. I told you, why don't you pause the video and see if you can get this 80 feet very quickly using that quadratic rule. Because I'm going to go through it right here. So using the quadratic rule, it says that f prime at 2.5 should be equal to 2 times a times the x value, or the t value here, plus the b value. The b value is clearly 0. There's no b value here. So that's 2 times negative 16 times 2.5, which gives us negative 80. So again, that's in feet per second. So you might look at this and see how much more quickly we're able to solve the problem than going through it this way, the long way. And that's why we come up with general formulas, so that we can do computations more quickly. However, this computation tells me nothing about the actual math that's going on in the background. This right here is the story. This is what you need to understand. This is what you can apply once you understand this up here. Okay, the last question is to find the momentum. Okay, P or rho or whatever, however they're defining it here. So find the momentum P. We define it as the weight, okay, in pounds, times the velocity. My V is lower here, and I'm assuming that in the problem they're meaning it. I am not entirely certain, but I'm assuming that they're meaning it as multiplication. Okay, and so V is the velocity in feet per second. So we've got W times V, so the solution for C is that the momentum at the time of impact will be equal to the weight times the velocity at impact divided by 32. And we need to make sure that the weight is in pounds and the velocity is in feet per second. So okay, we've got the weight, which is 20 pounds. We want to multiply that by the velocity, which is our velocity was negative 80. Okay, feet per 1 second. And then we want to take that whole thing and we want to divide it by 32. So we've got 20 times 80 divided by 32. And so that gives us negative 50 foot-pounds per second.